Okay, you can ignore the stuff that's over here. Again, I'm a little short on board space. Wanted to use up everything I had. On a graph of kinetic energy versus position. Now, it took us a long time to work through this because, and don't take offense, but nobody really understands slopes and areas under graphs and how to interpret them. So we want to interpret the slope of this graph, fundamentally, which means that we have to interpret the rise and the run. Slope is rise divided by run. So what's the rise between 2 points on a graph of kinetic energy versus position? What does that represent? What does the rise between 2 points represent? Well, the vertical coordinate of the first point would be the kinetic energy at the beginning of the interval between here and here. And the vertical coordinate of this point would represent the final kinetic energy, so that the rise represents the change in the kinetic energy. Now, this is no different than any other situation where you have something versus something else. The rise between 2 points is the change in the something on that's relative to the vertical axis. It's measured relative to the vertical axis. Okay, and the run is the change in whatever is measured along the horizontal axis. So whatever the graph, okay, you ask yourself, what does the rise mean? What does the run mean? And that tells you what the slope means. It's the average change, it's the change in this quantity divided by the change in this quantity. So in this case, it's the change in kinetic energy divided by the change in position. Now, that always has a phrase that goes with it. It's the average rate of change of this with respect to this. In this case, it's the average rate of change of kinetic energy with respect to position. That has a meaning. And there's a very clear meaning. Now, you know, the slope doesn't always have an important meaning that we want to interpret in terms of our calculus, in terms of the behavior of our kinetic energy function or whatever the function happens to be. But you always want to ask the question, because in almost all cases that you'll see, it does have an important meaning. And you got to think about what that rate of change means. To understand what that rate of change means, you got to ask yourself, what does it mean to divide the change in this quantity by the change in this quantity? Okay? In terms of this situation, the slope is change in kinetic energy divided by change in position. What's the change in kinetic energy? Well, if you know the work kinetic energy theorem, it's the work done by the net force. So that's the work done by the net force, which is the average force times your change in position. So it's the average net force multiplied by your change in position divided by the change in position, which is just the average net force. So the slope of this graph is your average net force between, well, on the interval between the 2 points, whatever that interval happens to be. It's a displacement interval, it's an energy interval. So there we have a profound interpretation. The slope of your kinetic energy versus position graph is a net force. We talk about how that can be applied in terms of what you've observed in lab. Okay, where have you observed a kinetic energy versus position? Well, you really haven't, but you've observed velocity versus position. Okay, if you observe velocity versus position, you can translate that into a kinetic energy graph by doing squared velocity versus position. And then if you scale your axis correctly, and I'm quoting details that you'd have to work through, but you could scale your axis accordingly, and the slopes of that graph would have to match the net forces. So if you also observed using computer interfaced probeware or whatever, the force, you could compare the graph of your force versus position with the graph of your kinetic energy versus position. And the forces that you get, for given x, the force that you get when you project up to your F versus X graph should be equal to the slope of your kinetic energy versus position graph. It's just one example of a profound connection. Okay, so what we've established then is that the net force versus position graph would be a derivative of this graph. It would represent the slopes of this graph versus position. Now, I'm not going to go into detail on that. I'm just trying to convince you that this is really important. It's really powerful and something that you will use. Okay? Now, we can also go to the kinetic energy graph and look at the same 2 points over here and talk about the area beneath the curve between these 2 points. And we'll do that in the next clip.